this episode, we're going to talk about outliers and anomalies in a way that keeps you from falling into the two most common beginner mistakes: treating every unusual point as garbage, or treating every unusual point as a thrilling discovery. Outliers are observations that look unusual compared to the rest of the data, and anomalies are observations that may indicate something meaningful, like an error, a rare event, or a change in behavior. Those two words get used interchangeably in casual conversation, but the mindset behind them should be different. An outlier is a description of how a point looks relative to others, while an anomaly is a claim about what the point might mean. In data AI work, unusual points can be mistakes that should be corrected, but they can also be the most valuable examples you have, especially when you are studying rare failures or rare risks. The exam often tests whether you can reason carefully about this balance, because cleaning data too aggressively can erase real patterns, while ignoring outliers can let errors dominate metrics and models. Our goal is to build a responsible approach that protects signal, respects uncertainty, and still keeps your analysis stable. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first step is to understand why outliers exist, because the correct handling depends on the cause, not on the appearance. Some outliers come from measurement errors, like a sensor glitch, a logging bug, or a unit mismatch that produces values far outside the plausible range. Some outliers come from data entry issues, like misplaced decimal points or swapped fields. Some outliers are legitimate but rare events, like a sudden spike in traffic, an unusually long response time during an outage, or an unusual transaction pattern during a special event. Some outliers are signs of a different population mixture, like combining data from two systems that have different baselines. Beginners often start with the idea that an outlier is a problem to remove, but removal is only justified when you have a defensible reason that the point does not represent the phenomenon you care about. If the point represents reality, removing it is not cleaning, it is censorship of the data. The exam often rewards answers that emphasize investigating the cause before acting, because responsible outlier handling begins with curiosity and caution rather than automatic deletion. It is also important to separate the goal of detecting outliers from the goal of detecting anomalies, because those goals lead to different decisions. Outlier detection is often about protecting statistical summaries and models from being distorted by a small number of extreme points. Anomaly detection is often about finding the extreme points on purpose, because those points could represent threats, failures, fraud, or unexpected behavior. In other words, in one case you are trying to make your analysis stable, and in the other case you are trying to use the extremes as the primary signal. A beginner trap is to apply outlier removal thinking to an anomaly detection task and accidentally delete the very events you want to detect. Another trap is to apply anomaly hunting thinking to a forecasting task and treat every extreme point as meaningful when some are simply measurement noise. The exam may describe a scenario where the goal is to detect rare harmful events, and the correct response often involves keeping and analyzing unusual points rather than removing them. Your job is to match your outlier strategy to your mission, not to follow a single rule. A responsible approach starts with defining what normal means in the context of your data, because outliers are only outliers relative to some baseline. Normal can differ across subgroups, like different regions, device types, or time periods, which means a point that is normal in one subgroup can look extreme in the aggregate. This is why outlier detection can go wrong when you ignore stratification and treat the entire dataset as one homogeneous blob. For example, a latency value that is typical for a remote region might look like an outlier compared to a local region, but that does not mean the value is wrong. If you remove those points, you may accidentally erase the reality of that subgroup, making your model less fair and less accurate for that region. Another way normal changes is over time, like during seasonal peaks or system upgrades, which can create legitimate shifts in distributions. Beginners often use a single global rule for outliers without checking whether the data contains multiple modes or multiple baselines. On the exam, If a scenario describes multiple environments or subpopulations, a mature answer recognizes that outliers must be evaluated within context. Responsible handling includes defining normal in a way that respects that context. Many beginner-friendly outlier detection ideas are based on distance from a center, like using the mean and standard deviation or using percentiles, but the deeper lesson is not the formula. It is the sensitivity to distribution shape. If your data is roughly symmetric and not heavy-tailed, distance from mean rules can work reasonably well as a first pass. If your data is skewed, has long tails, or contains natural spikes, a mean-based threshold can label too many points as outliers or miss meaningful extremes. Percentile-based thinking, like focusing on unusually high or low percentiles, can be more robust because it does not assume a particular shape. Another robust approach uses the median and the spread around the median, because the median is less pulled by extreme values. The exam may not require you to compute any of these thresholds, but it may test whether you understand that different distributions require different thinking. If a scenario mentions skewed data or heavy tails, a correct answer often involves caution about mean-based rules and an emphasis on robust summaries. The key is to avoid applying a one-size-fits-all detection rule, as if every dataset behaves like a neat bell curve. Once you flag potential outliers, the next step is to decide what to do, and this is where responsible handling becomes more than detection. A common beginner impulse is to delete the points, but deletion is only one option, and it is often the most destructive if done without proof. Another option is to correct the point if you can identify a clear error, like a unit mismatch or a known logging bug. Another option is to cap extreme values, sometimes called Windsorizing, which reduces the impact of extremes without pretending they never happened, though it still changes the data story. Another option is to transform the variable, like using a log scale, so that large values do not dominate analysis while still being represented. Another option is to keep the points but use models or metrics that are robust to extremes, which is often a better strategy when extremes are legitimate. The exam tends to reward choices that preserve information unless there is evidence the points are invalid. It also rewards acknowledging tradeoffs, like that capping can reduce distortion but can also hide rare but important variation. A responsible handler asks, what action reduces harm without erasing signal? One of the most important implications of outlier handling is how it changes your performance metrics and model evaluation, because outliers can dominate averages and distort your sense of improvement. In regression, a few extreme errors can inflate our MSE dramatically, making a model look worse than its typical performance. In classification, outliers and input features can produce extreme scores that drive threshold decisions, potentially creating false alarms or misses. If you remove outliers from both training and evaluation sets, you might produce artificially optimistic performance that does not reflect real-world deployment, where unusual cases are part of the environment. Beginners often clean the test set to make the numbers look nicer, not realizing they have reduced the realism of the evaluation. A better approach is to be clear about what kinds of cases your evaluation represents and whether outliers reflect real-world conditions. If a scenario mentions that anomalies matter to the mission, a correct exam answer will usually argue for keeping those cases in evaluation so you can see whether the system handles them. Outlier handling is not just data cleaning. It is a decision about what reality you are modeling. Another critical issue is that outliers can come from label problems rather than feature problems, and label outliers can be even more dangerous because they can teach the model the wrong lesson. If a rare case is mislabeled, it might look like an outlier because the features do not match the label, but the real problem is the label, not the features. In classification tasks, mislabeled examples can confuse the model, especially when the dataset is small or when the mislabeled points are extreme. If you respond by deleting the outlier features, you might be deleting the rare cases that truly matter, rather than fixing a labeling error. This is why responsible detection includes considering whether the unusual point is an unusual feature value, an unusual label given the features, or an unusual combination that suggests data quality issues. The exam might describe a model that performs poorly on a small set of cases and ask what could explain it, and label noise is a strong candidate. A mature response includes the possibility that outliers signal labeling issues rather than representing invalid data. In other words, sometimes the outlier is your data process telling you it needs attention. Outliers also interact with fairness and representativeness, because what looks like an outlier can sometimes be a minority pattern that is underrepresented in the dataset. If you have few examples from a subgroup, the subgroup's normal may look like the global outlier because the global distribution is dominated by the majority group. If you remove those points, you can unintentionally erase that subgroup's reality and make a model that works only for the majority. This can happen even when you are not thinking about demographics, because subgroups can be device types, network conditions, or usage patterns. The responsible approach is to check outliers within strata where possible, so you can see whether the point is unusual within its peer group or only unusual in the aggregate. The exam will often reward this contextual thinking because it aligns with good sampling and bias awareness. It also reinforces that outlier detection is not only statistical, but also about understanding the data generating process. If the data comes from multiple sources, a so-called outlier might simply belong to a different source baseline. Removing it would remove information about that source, which is often exactly what you do not want. Anomaly detection as a mission also deserves careful thinking because it changes what you mean by success. If you are using a model to find rare harmful events, you should expect that anomalies are scarce and that labeling them may be difficult. Many anomalies will be novel, meaning they do not match any previously labeled examples, so you are dealing with uncertainty by nature. This is why anomaly detection often relies on defining normal behavior and flagging deviations, rather than learning the anomaly class directly from many examples. The exam may describe a situation where the anomalies are unknown or evolving, and the correct reasoning often involves emphasizing patterns of deviation rather than expecting perfect labeled training. In these cases, outliers are not something to remove. They are the outputs you are trying to surface. The responsible question becomes how to tune sensitivity so you catch meaningful deviations without overwhelming people with false alarms. That is a threshold and trade-off problem similar to classification metrics, but with more uncertainty about ground truth. Recognizing that difference is part of responsible thinking. A related beginner trap is assuming that anomalies are always extreme in a single variable, like the largest value in a column, when in reality anomalies are often unusual combinations of otherwise normal values. For example, a login time might be normal, and a location might be normal, but the combination of that user and that location at that time might be unusual. This matters because simple outlier rules that look at one variable at a time can miss multivariate anomalies. It also matters because cleaning based on single variable thresholds can remove points that are extreme in one dimension but perfectly normal in context, while leaving points that are suspicious only in combination. You do not need to implement multivariate methods for this course, but you should understand the conceptual limitation of one-dimensional thinking. Exam questions may hint at anomalies that involve patterns, not just single values, and your response should reflect that you understand anomalies can be contextual. A mature answer recognizes that unusual does not always mean huge, and huge does not always mean unusual in the right way. This protects you from treating outlier detection as a simplistic high-value filter. Another responsible practice is to avoid making outlier decisions solely to improve metrics, because that can produce models that perform well on paper but fail when reality is messy. If you remove cases that the model struggles with, your evaluation will improve, but your system will become brittle because you trained it to live in a cleaned world. A beginner may feel tempted to remove hard cases because they feel like noise, but hard cases are often exactly what the real world will deliver. A better way to improve a model is to understand why those cases are hard, whether they represent a different regime, whether more features are needed, whether labels are inconsistent, or whether the model form is mismatched. In some tasks, you might legitimately scope the model to a domain where it is valid, but that scoping must be honest and reflected in how the system is used. The exam often tests for this honesty by offering answer choices that remove outliers to increase accuracy without addressing the underlying data process. The correct choice is usually the one that investigates and accounts for them rather than sweeping them away. Responsible outlier handling is about fidelity to the problem, not about prettiness of results. To close, detecting outliers and anomalies responsibly means you treat unusual points as questions first and as actions second. You learn that outliers describe unusual observations, while anomalies suggest potential meaning. And confusing the two can lead to deleting the most valuable signal or chasing random noise. You learn that causes matter, with outliers arising from errors, rare legitimate events, population mixtures, and labeling problems, and each cause calls for a different response. You learn that outlier rules depend on distribution shape and context, and that subgroup baselines and time shifts can turn global outlier detection into accidental bias. You learn that handling choices like deletion, correction, capping, transformation, and robust modeling each carry trade-offs, including how they affect metrics and generalization. Most importantly, you learn that responsible practice avoids cleaning the world to fit the model and instead uses outliers as diagnostic evidence about data quality, model limitations, and real-world variability. When you can explain these trade-offs in plain language, you are ready for exam questions that try to tempt you into simplistic removal, and you are also building the mindset that protects real systems from failing precisely when the unusual happens, which is often when the stakes are highest.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.